Yes.
Is on?
Start.
Just a second. Hi, good morning, everyone. Yeah, since I'll be going to talk with you guys for a couple of days, I thought it's good I start to introduce myself a little bit and also talk about my institution, and then we start talking about the lecture material. So first, I will talk about the IPCC report. So essentially, we'll focus on some fundamental concepts about the IPCC report. We only have time for a very small proportion from the report. And then I will use some case studies in the next couple of days to talk about drought, talk about flooding, and different things. So yeah, I guess maybe first just introduce myself a little bit. Yeah, again, first I want to apologize for being late. Yeah, somehow the driver forgot to pick me up this morning. Currently, I'm a professor at Indiana University, Indianapolis, which is located in the center of the U.S., very close to Great Lakes, very close to Chicago. If you know, the city is about 3 hours. So that's what it looks like in my city center. So I came from China originally. I got my bachelor degree from Hebei University a long time ago now. And after I got my degree, I got a bachelor degree. I got a fellowship. I came to U.S. for master degree at the University of North Carolina at Greensboro. I spent 2 years there and finished my master degree, and then I went to University of Virginia for PhD, majoring in environmental science. And then after that, I spent about 3 years as a postdoc researcher at Princeton University in C1 Environmental Engineering Department. So similar to many of you guys here. And then after that, I got a fellowship from Australia, University of New South Wales. It's called Vice Chancellor Fellowship for 3 years. So I moved to Australia there, but only like a half year. But when I was there, I got a job offer from my current university. So this is permanent position. So this is just like a 3-year position. So I just gave up the fellowship and moved back to US, and I was here since then, for about 11 years now. So that's kind of my trajectory. And so, over the years I've been doing, I think, a good research, got recognized at different level, like from my university. I got the President Bicentennial Medal. It's only a few from the university got that. And the national level, I got called a National Science Foundation Career Grant. So that's also a big honor too. And internationally, I have been writing many papers, and they got used quite often. So I got recognition as a highly cited researcher from 2013 and last year as well. So yeah, I guess the point here is not bragging myself. It's really just to give you the idea. If I can do it, everybody here, you can do it as well. Right? I start from a kind of academically like a modest status. Like my university is good university, it's a good state university, but not the very top ones in China. So, but I can still, work hard, dream big, and keep working hard until you can, achieve the dream you want. I guess the idea is, if you have a good dream in your academic world, keep doing on that regardless where you start. So the field of my research is called eco-hydrology. Simply speaking, is basically I'm looking at the interaction between vegetation dynamic and the water cycle. So there is a two-way interaction here, and the interaction is controlled or influenced by the soil condition, but also by the atmosphere condition. So that's make the interaction more complex. So I'm looking at this interaction from different scales. From individual plant scale all the way ranging to global scale. So in next couple of days, most of example will talk about as a larger scale ecosystem to global scale, but we do look at things at a different level. And the key question in my group is really we try to look at the impact of climate change on the interaction between vegetation and the water across different scales. Over the years, my group has been publishing widely, like in different journals. A lot of them are in the top journals, nature groups. So again, that's the same idea, right? So I guess keep working hard, dream big, and you should be able to achieve a lot of success along your career. So enough about me. And this is a university I work now. Right? So that's it's called Indiana University Indianapolis. So it's one of the several campuses belong to Indiana University. So there are several like UC system, UC Berkeley, UC LA. So there are different campuses. We are one of them, and we have about close to 30,000, 25 plus thousand students on our campus, and it's quite diverse. You can see there are students from 100 plus countries, so it's actually quite a diverse body. In fact, even our chancellor is actually from the Indian region, Dr. Rasa Ramahan. So I think she graduated from one of the IIT schools. So we have a lot of degrees, right? Close to 400 degree certificate program, and we have in total like 17 schools. And in terms of research funding, there every year a lot of research money coming to the campus. So we have a School of Medicine of Indiana University located in our campus, but when we count for the research funding, typically they are separated because they get just so much money. So it's they kind of independent in many ways. And we have a lot of research centers and research institute. So I'm within. So the university is an urban campus, right? So it's in the capital. So it's we consider it's a premier urban campus in the US. So because Indianapolis is the capital of the state, is quite culturally diverse and has a lot to offer. There are different rankings. Again, the university is not the one you hear every day, but it's a decent, it's a research intensive university. So I'm out of the 17 schools, I'm within School of Science. That's one of the 17 schools within our university, and we have 6 departments. So biology, chemistry, math, physics, psychology. So I'm in the department of Earth and environmental sciences. So just a couple of slides about this particular program. Right? So we have a kind of a different bachelor, and master, and PhD degrees. We have a bachelor degree in geology, and also we have a bachelor degree in environmental science. We have master degree in geology, and then PhD in applied earth science. So that is a interdisciplinary PhD program. And in the past, I have a student that has an engineering background. I have a student with a biology background. I have a student with a physics background. Right? So it's actually quite diverse PhD program. You can have a student from very diverse background. So I guess the idea talk about this is, I know you guys, some of you guys are master students, some are PhD. Right? So if you are interested in pursuing your degree for a master's student, for example, you can talk with me about the planning program here. Right? So in US, in general, if you are working on a master or PhD program, you always get fully funded. Right? So if we don't have money, we don't take you. Right? So that's typically the program, how program runs. You don't have to pay yourself, like myself. Right? I get fully support doing my master and PhD degrees. And for this department, we have this relatively small department. We have 13 faculty members as a specialty in different areas, some in hydrology, some in geochemistry. We have a lot of very advanced instruments and techniques like people use in different fields of geoscience. Personally, I have two isotope instruments using for hydrological investigation. So our program has about 100 undergraduate students and about 30 graduate students in our program. And all the faculty has research fundings come from the National Science Foundation, NASA, USDA, USGS. So there are pretty diverse research within the department. So yeah, I mean, just very brief to talk about my journey and also the university I work with. So if you want to pursue an advanced degree, or if you're a faculty member here, you want to doing Fulbright, we do have every year there are several Fulbright scholars from different schools in my university. So yeah, that's just a very brief background. And then my plan is we'll go to the IPCC report. We'll just touch on some of the important concepts today, and then later we'll talk about some case studies. So how many of you guys heard of the IPCC reports? You will raise your hand. Good. Good. Yeah. So how many actually read IPCC report? Have you read any of IPCC report? Not really, right? So that is interesting. Yeah, when I teach my own class in my university, right? So actually, there are even less percentage of the students actually know IPCC report. They never heard of IPCC, right? So I mean, for you guys, majority actually heard of IPCC report. Right? That's good. But very few actually have the chance to read the report itself. Right? So IPCC stands for Intergovernmental Panel on Climate Change. That's IPCC. Right? So it's basically a United Nations body. Right? So that's their function is to try to. We'll talk about their function in the next slides in more detail. But really, this United Nations body try to assess the science related to climate change. That is the IPCC stand for. Right? So, and they're in their own work, that's IPCC talk about their own role. Right? So basically, they will take a very comprehensive approach, take a very objective approach, and a transparent approach, try to assess all the available information in the literature related to climate change. So that's the kind of aim of this body. And they try to stay neutral in terms of government policy, right? So, but they do keep policy implication in their mind, right? So that's the idea. They try to. So that is the role of IPCC. This is kind of a brief history of IPCC. So IPCC was established in 1988. So that's a joint establishment by WMO, World Meteorology Organization, and UNEP, United Nations Environmental Program. So these two agencies from the United Nations established the IPCC. And then, as time goes by, the milestone of IPCC are these ones. FAR refer to the first annual assessment report, second assessment report, and then third assessment report. So from the fourth one, they change to assessment report 4, 5, right? So things like this. Right? So that's a kind of timeline of different report, which year they were reported. And then they have some kind of a special report. So special report 15 basically talk about, if we have a 1.5 degree Celsius temperature increase, what the world look like. Right? So that's kind of a special report. And the most current, the most updated report is AR6. So that's produced in 2022. Right? So that is kind of a timeline of IPCC report. You can see as time goes by, the scientific literature related to climate change has been expanding dramatically, and so that's why people need to access more and more information. That's why IPCC report, every report take about 5 years, 5-6 years. So because there's a lot of information people have to put in together, so it's take time. So this one is from IPCC report. So in my class in the university, I use IPCC report because it's public available, and so it's you can freely download from their website, right? So it's actually you can download individual chapter of the whole report. So it's actually very handy to have that. And all the figures I show you here is actually from the report. It's all public available. You can access that. And this is kind of the procedure IPCC produce their report. They do scoping, they prove the timeline, and then each university, each countries will recommend authors for IPCC report, and then they meeting together. It's a long process. There's a lot of meetings involved, planning, review the report, and the final proof. So for final proof, they actually prove line by line. Everybody has to agree. It's actually a very tedious process. So this is the kind of structure of IPCC report. They have really like 3 working groups. The working group 1 is mostly focused on the physical science, and then the working group 2 is focused on the impact of climate change, and then working group 3 is talk about what the mitigation strategies you can use to mitigate the climate change impact. And then there is a task force specifically for doing the inventory for greenhouse gas emission. So they are the kind of 4 major groups within IPCC doing things, and each group will produce their own report. Right? So the report I'm using mostly the first group is the physical science one. Right? So talk about what's the most updated understanding of the climate change information. So they try to have a kind of intervene between the plenary session is that everybody meet together to discuss the final report, and the bureau is basically the different groups. So there is an interview between the policy side and the science side. Try to they try to stay neutral, but they try to make human influence on climate system is clear. So in the AR6, AR6. Language is even more stronger. And then we talk about the more we disrupt the climate system, the more risk we are facing essentially. And then the third one is a kind of a positive uplifting note to talk about. We do have means actually to mitigate the impact if we do things. Right? So that's kind of the 3 key messages from IPCC report. And their biggest achievement, we probably know, is the group as a whole. They were awarded the Nobel Prize in 2007 as a recognition of their role for informing people about the impact of climate change. So this is what AR6 look like. Right? So that is AR6, the physical science report. So you can see, I give you an example of the chapters. There are 12 chapters. You can see there are more than 2,000 pages. It's a very large report, right? So that's why nobody read it, right? So it's just very dense report. But to me, it's actually the best scientific literature regarding climate change, right? So even they are really trying to put in a way can be digested by anybody, but of course it's written by scientists. It's still dense sometimes. It's not very easy to read, but it's not like terribly hard to read. So I would suggest all of you guys, if you're doing climate-related research, that should be our starting point. Actually, they are written by leading scientists in the field. They actually doing the literature review already for you, right? So they already tell you what the most updated status of a certain area, right? If you're doing research in any area, you should check what's the current status. Then we can just talk about some of the major concept, the key concept in terms of climate system, right? So the first one is basically the difference between weather and climate, right? So in climate deniers, right? So they always talk about sometimes, today is so cold, why we talk about climate change, or this winter is so cold, why we talk about climate change. So because they try to, in a way, or they just get confused about the weather events and the climate events. Right? So when we talk about the weather, we talk about the atmosphere conditions, like a very short time scale, right? Days, weeks. So, but when we talk about climate, we really talk about average weather condition over a very long time. And for the WMO, they define climate, you actually have to talk about average over 30 years period. Right? So we are actually talking about the moving average of the weather condition, using long-term average, like 30-year moving average. Right? That is a big difference between weather and climate. Right? So, but even weather, right? So some people talk about today is super cold. Why we talk about global warming? So actually, climate change is not only introduced just warming itself, right? It's really the big variability of the climate, right? So in Indiana, for example, we are in Midwest in the US, right? So in winter is mild, it could be cold, but there are some days could be super cold, right? So part of the reason for that is because of the changing climate. They make the polar vortex very strong, right? So the cold air sometimes can escape the polar vortex and get into the Midwest region, right? So climate warming actually sometimes could bring cold weather. So that's sometimes it's counterintuitive, but that's true. So the second important concept is radiative forcing, right? So really when we talk about how things warming the climate or how things cooling the climate, we really talk about their radiative force. Right? So radiative forcing in definition is basically a measure of the energy balance change in responding to whatever the disturbance we're talking about, either more CO2 you put in the atmosphere or more aerosol you inject into the atmosphere. Right? So that's we are talking about the net change in energy balance. So when we talk about positive radiative forcing, essentially we are talking about this is the warming of the climate. If we talk about negative radiative forcing, we are talking about this is the cooling the climate. Right? So in our climate systems, most of all the greenhouse gases, right? So they are very strong. They have a very positive, very strong warming potential because they have a positive radiative forcing. And for the ugly one, almost the ones like yours is also negative radiative forcing overall, but the aerosol is kind of the factors the most powerful like a cooling radiative forcing, so they can cool the climate. So that's why a lot of people talk about the geoengineering. Right? So if we get to the point, the warming is out of control, you have to do something. Right? So one thing people talk about is really the kind of injection of the aerosols into the Earth's atmosphere. So that will have immediate cooling. Right? So of course that has unknown consequences. Right? We don't know how much the impact on human health, for example. And so people, that's our kind of last resort. Right? You don't want to do that. The most effective is still we're cutting down the emission. Right? We're cutting down all the greenhouse gases. And we try to not go to the resort. So that's but that is basically when we talk about the climate forcing, you need to know what is the radiative forcing, what that's referred to. So feel free to stop me anytime if you have questions. Right? So I need to be interactive lectures. So another important concept basically is positive and negative feedbacks is the climate system. Right? So this one is different from radiative forcing. Right? So when we talk about positive and negative feedback, we are really talking about the kind of the process. If we talk about the positive feedback, we are really talking about like a process accelerating whatever the process already going on. And the negative feedback talking about the process will slow down or put a brake on the process, on the warming, right, in this case. So this is also a figure from IPCC report to talk about the different positive and negative feedbacks in our climate systems. Right? So positive ones are typically easier to understand. For example, when we talk about water vapor, as why we call water vapor is a positive feedback, because if you have a warming happens, right? So then you will have more evaporation. More evaporation will basically produce more water vapor in the air, right? Because water vapor is a very strong greenhouse gas, right? More water vapor in the air will make the warming even more quicker, right? So that's why we call positive feedback. Is actually accelerate the whole process, right? So but if we think about the negative feedback, basically we have to think about that is the process actually slow down the warming, right? So for example, for long wave radiation, right? So that's essentially is because Earth is a black body, right? It's always emit energy, right? But if you warm in the Earth's body, so there will be more emission, the energy emission. But more energy emission means less heat or less energy in Earth. So that means the warming will be slowed down, will be less further warming. Right? So that's why it's called negative feedback. It's really the process actually break down or slow down the warming. Right? So that's a big difference between positive and negative feedbacks. Any questions about the positive and the negative feedbacks? So anybody can describe, for example, for snow, ice, albedo, right? So that is actually positive feedback. Can you try to describe why that is a positive feedback? So you can start. So typically we will start from warming, right? So warming will make certain changes in snow and ice albedo, and that changes essentially should accelerate further warming. That's why we call it positive feedback. So, but somebody can describe in detail what the process look like. You don't be afraid to, don't say that. Yeah, just have a try. Or we can do together, right? So if we have a warming condition, right? So how that will impact the snow and ice albedo, increase or decrease? Yeah, this one I can't hear you. Yeah. Yes. So if you have a warming condition, what's the impact for albedo? Is it increase or decrease? If you have a warming condition, that will melt the snow and ice, right? So when you have a melting of snow and ice, do you increase or decrease albedo? What is albedo, I guess? It's a reflection, right? So if the ice is gone, whether that's increase or decrease albedo? Increase. Right, it's increasing, right? So, if you have a warming condition, the snow and ice cover will be lower, right? So that means you increase the. Oh no, sorry. So if you have a less ice, whether that increase or decrease albedo. Albedo is a reflection, right? So if you have ice, actually it's very good at reflecting the energy back, right? If you have less ice, that's a higher and lower albedo. So less will be reflected, right? More will absorb, right? So that will be less, the albedo will be less, right? So it's actually lower albedo. But lower albedo means less will reflected, more will be absorbed. So that will be make the melting even more and the albedo even lower, right? So that's why it's a positive. It's actually make the albedo like less and less, but also the warming higher and higher, right? So that's why we call it is a positive feedback. Yeah, thanks for trying. Yeah, that's good. So I guess when we talk about the future climate predictions, right? So sometimes it's very hard to do just because a lot of the complex feedback within the Earth system, like a clouds, you can see, there are both positive and a negative component, right? So it depends on the location of the clouds, depends the type of the clouds, right? So some clouds has a positive feedback, some clouds has a negative feedback, right? So that's why climate itself is quite complex when you predict the future climate response. So later we will talk about the complex response. We will touch that again. But the point here is really try to understand, what is positive feedback, what is negative feedback, and you can try to use your word to describe what look like, right? So maybe, for example, for air CO2 exchange, right? So this one, for example, if we have a more CO2 like in the atmosphere, right? So that means the exchange will be more, right? So there will be more CO2 basically stored in the ocean, right? So there will be less in the air, right? So that's why is a negative feedback, right? So that's is actually kind of reduce slow down the process, and the positive is accelerating the process. Just make sure the major difference between these two. So for different IPCC report, there are different policy contact. So the first IPCC report, FAR, so that's why it's actually is a foundation for the UN Framework Convention on Climate Change, UN by IPCC. So that's why it's actually is a very large framework people use to fight climate change. So FAR, the first assessment report, is a foundation for this framework. And the second assessment report is actually the foundation for the Kyoto Protocol. So that is the first major international agreement fighting climate change. That is called the Kyoto Protocol. Right? So what's the second one? This is the first one. What's the second one? Or the most recent one? So the first one is Kyoto. What's the second one? What's the recent one? What's that called? So the second one is called Paris Agreement. That's 2015. That's the most recent one. Right? So that one is basically rely on the L04 and L05 report. So both these reports provide a foundation for the Paris Agreement. So the major difference is for the Kyoto Protocol is almost like a volunteer participation, right? So there's no very clear enforcement. But for Paris Agreement is more structured, try to make people really doing the work, right? So it's a little bit much more rigorous in a way, try to get the results. So the really the goal of Paris Agreement try to let the whole human society as a whole try to fight climate change, let the temperature below 2 degrees C, and hopefully below 1.5 degrees C compared to the pre-industrial period. So that's the goal for Paris Agreement. Of course, some scientists already worry, even right now, we may already pass the 1.5 degree mark in the sun for the end of the century. So that's definitely discouraging, but many think we still possible for the 1.5. But I mean, the point is there's no magic number like 1.5, 1.6, 1.7, or 2, right? So really, the more we do now, the quicker we do now in terms of the reduction in emission, the less variabilities, the less harm we make for our future generations. Right? So science is very clear on that. So it's really how do we actually react to this. So, in ER6, there are some kind of a newer concept, new foundations people talk about. Some talk about earlier, people emphasize again. Like for example, people talk about the baseline, people talk about reference period, people talk about anomaly. Right? So here I just give you a definition for this. So baseline basically we refer to kind of the average from the reference period. That's our baseline, right? By name, you can see that that's the ones we compare to, right? That's our baseline. And the reference period, basically, you talk about a period you compare other period with. So that's the reference period. And anomaly is really talk about, remember, the anomaly is not like, English meaning in terms of, is very different from others. But anomaly in climate scenario here is has a specific meaning. Right? So really, when we talk about anomaly, we talk about the difference between the current observation from your baseline. So the difference is anomaly. Right? In climate reporting, a lot of time we always use anomaly to do the trend. Right? So here I'll give you an example. So you can think about why we don't use the raw value, why we use anomaly. Right? So here is a different climate model predictions about the temperature trend from 1850 until the end of the century. So each line refer to each individual model, and then you have observations here. Right? So and then there are different ways to present that. But I guess based on this, based on your understanding of what is the baseline, what is the reference period, what is the anomaly, why people tend to prefer using anomaly rather than this is absolute value, so the kind of raw data, and this is anomaly. Why people use this, not this? So what's the advantage of using anomaly in presenting the climate data? So basically, you're talking about minimize the variability, right? Highlight the trend, right? So yeah, that's exactly one of the major reasons people use that, right? So you can say for individual model output, right? So they don't necessarily agree with each other exactly, right? So every model has their own bias. Some maybe perform better in certain region or certain time period, and the others may perform better in other scenarios, right? So they all have their certain bias, right? So, but you can say, if you use anomaly, essentially are talking about you use, even they have their own bias, right? So because you use the observation matters and reference period, you actually get rid of that own bias in doing that, right? So, but by doing that, you can actually highlight how things are changing more clearly, right? Rather than look at the variability here, right? So that is a key reason people using anomaly rather than the like absolute value, right? So because all the observations, all the models, they have their own bias, right? So the same for observation, right? So many people are measuring temperature, right? So across the global scale, but you may use a different thermometer, and they may not calibrate exactly correctly, right? So they may not reading exactly the same. When you're using different data set to do the global average, there may be a bias in each different data set, right? But if you just keep using the same thermometer over a long time, even it's not reading correctly, but there's some systematic error. But if you're using the trend, using the difference, and you get rid of that small error, you can then compare from this location to this location in terms of the trend. You don't need to worry about the individual thermometer or how accurate they are. Right? You're talking about the trend. Right? So that's also part of the reason people prefer using anomaly, because you highlight the trend, you can then use a different data set, compare different regions, see their trend is faster or slower compared to different regions. Right? So yeah, just make sure you understand the power, the advantage of using anomaly rather than using the raw value. And also I want to introduce the concept. You need to know what is the CMIP6. Right? So CMIP6 stands for Coupled Model Intercomparison Project. Right? So that's basically by far the largest group effort. People try to compare different models and try to see how well they agree with each other, right? How well they agree with each other in terms of which region, where they are. Right? So it's basically a comparison of a comparison. It's a very large comparison. You can see there are already different modeling groups. They actually making the comparison. For example, some group maybe focus on ocean, some focus on land surface, and some maybe focus on paleoclimate. Within each group, they already have many models they compare with each other. And then the CMIP is basically you compare all of them all together. So that's why it's very large group effort doing the model comparison, make sure we have the most updated understanding of our model predictions. Right? So the most current version is CMIP 6. Right? So that's typically CMIP is the same status as the IPCC report. We have an IPCC report AR6. So that's why CMIP is also on their 6th version. Right now, CMIP scientists are doing on the CMIP 7 now, and people also try to work on AR7 as well. Right? So they always parallel to each other. So another important concept I want to highlight is climate variability. Right? So we need to know climate does has their own variability. Right? So yearly variability is always there. So regardless what parameter you are looking at, either temperature, global temperature, regional temperature, or you talk about like a CS volume or like a coverage, they all changing year by year. Right? So that's the inherent nature of a climate. Right? But we need to recognize that because for example, we know climate has a big variability, but if you use very small data set. For example, we know global temperature is increasing, but if you only use maybe 5-year data from here, you can actually have a conclusion global temperature is actually declining. Right? So the same here. For UK summer temperature overall we know it's increasing, but if you only pick these 10 years, if you run time series analysis, you'll get a conclusion UK temperature is still declining. Right? So, I guess the point is when we think about the climate, you have to think about long term. Right? So, sometimes if you use like a short term data, you could have an opposite direction from the long term trend. Right? So for CS extent, we know it's declining at a global scale. But if you look like a small period, that's blue line like here. If you run the Mankanda like a time series using this data set, your conclusion is the CX is actually increasing. So that's incorrect for like a long-term trend. So that's the point of climate variability. And also, even with climate variability happening, right now, based on the record we have from other continents, we know there are called emergence of a climate change signal. Even with the climate variability we have for other continents, we actually see the climate change signal is there. Right? You can see. Right? Sure, there are different continents, the climate variability is different, but in North America, in US, right, for example, the climate variability is actually much bigger compared to South America or Africa. Right? So their variability is actually smaller. Like Europe and America, actually, they have very large climate variability. But even with the variability, we actually saw the climate change signal. Right? So it's actually quite clear there. So yeah, that's this last two slides really just try to emphasize. We know there is a variable climate, right? It's always changing. That's why we use a long-term data set. We don't use like a small section of the data to look at the change. But also, even with the variability we know as it is, we actually clearly see the signal, the climate change signal from all the continent, right? So that's kind of a key message here. So, when you read IPCC report on climate record in general, we know there are always uncertainties in our future predictions. So here, IPCC summarize, kind of the major sources of uncertainty in terms of both observations and the model or projections. So for observations, like I mentioned, you could have, the instrument wrong or systematic error, right? Could be random, inherent randomness in climate system, but also could be instrument problem, right? So that is uncertainty. But for future projections, there are actually different group of uncertainties there. The biggest one, I would say, is the radiative forcing uncertainty. So that basically means we don't know how much more CO2 will emit in the future, in terms of human society, right? So we may cut them very big, but we may do business as usual, right? So, that is the largest uncertainty in climate projection. And another is the climate response uncertainty. We talk about, there are positive, negative feedback in climate system. So climate response always has some uncertainty. For example, the CS, the degree of CS accelerating their disappearance is actually faster than scientists predict, right? So that's actually a surprise. So that is a climate response uncertainty. So uncertainty doesn't have to be one way or not. It's not like it could be faster or could be slower. Right? So that is uncertainty. And also the natural variability, like climate has their own natural variability. Right? So for example, there could be a big volcano eruption somewhere. Right? So that one, we know the large volcano eruption has a very large impact on climate systems, right? So, like in Philippines, like the one erupted in 1997, right? So that actually has a global cooling effect for about a year, right? So it actually has a very large global consequence. We, as a human being, we never be able to predict, exactly where the large volcano eruption will be. We can predict maybe shorter time scale within weeks, months, from the seismic activity, but you can't do the long-term projection, right? So that is uncertainty. And then the interaction between climate variability and the radiative forcing, that's another uncertainty, right? So the last one basically is the model itself, right? So model is not perfect, right? So it's always a simplification of the actual system. There are always uncertainties there, right? So, that's basically the kind of the sources of uncertainty in future climate projections, the major source. So here, just give you the kind of a model projection uncertainty example. That's a figure from IPCC report. So you have a global temperature projection, regional temperature, and that has rainfall projection. So really, the key message I want to show you here is, there are different scenarios. The lower emission scenario, the higher emission scenario. Each scenario, you can see there are very big spread from individual models. Right? So, you can say one message you can get is if you compare temperature, global temperature and regional temperature, the regional temperature tend to have a bigger spread. So the uncertainty is larger. And also, if you compare temperature and the precipitation, you can say the temperature, the uncertainty is much smaller. The precipitation is much bigger. Right? So, depends on the climate variable you are looking, the uncertainty is different. And also depends on the global temperature prediction or regional temperature prediction, they are different too. And also, it depends on how far you look into the future. Right? So, if you look at more like a near future or far future, you can say even further away you are predicting, the more uncertainty that will become. So that is another message. So that's why for IPCC report, we never just use a single model result. We say, okay, the future will look like this. That's not good, right? So we're actually using a term called sampling. Right? So basically means you actually average all the available model predictions. You actually, make you can say you average all of them, you get, results. So that's tend to be reduced much significantly. So that's the concept in sample, right? So you don't take prediction from any single model. You're actually using the average. So that's in simple word about in sample. But in sample you can do many different ways. You can actually, in sample the most common one you can do the kind of just in sample the output, model output. But you can also in sample the initial conditions. For different models, you have a different initial condition. You in sample you make average all of them first, and then you run the model. That's the initial condition in sample. So you can also in sample the parameters of different models. There are different ways people do in sample. But the idea is, you never report results from one single model. You're actually always doing that in average manner. So maybe let's finish this 2 slides. We'll finish. So because we know uncertainty is always here in IPCC or in climate system. So in IPCC report, people try to deal with uncertainty in a very active manner. Right? So there are 2 ways people do deal with uncertainty. One is a qualitative, right? So that's a qualitative way. So people use confidence level, right? So whether what level of confidence, you could have a very high confidence, you could have a very low confidence. So that's a qualitative way to deal with uncertainty. So how do you do that? So this basically just based on the number of evidence you have, and then how variable between all the evidence. If I have a lot of evidence, robust evidence, and all the evidence point to one direction, high gradient, so that means you have very high confidence. But if you have a very limited evidence for certain things, and also even with this evidence, they, from all over the place, low gradient, so it will be very low confidence. And then there will be some in between, right? So you have a lot of evidence, they don't agree with each other very well. That's a kind of a medium kind of evidence, medium confidence, right? So there are a lot of in between. So, but this way is more qualitative, right? So it's not based on numbers, really just based on how many evidence you have, what level of agreement for this evidence. And then another better way for quantifying uncertainty is using the likelihood. Essentially, I'm using probability series, right? So that's if you have a probability of 99% above, we call virtually certain, right? If you have a 0.1% probability, we call exceptional unlikely, right? So and then they're based on the probability threshold, people call virtually certain, very likely, right? So, when you're reading IPCC report, when they use this word, they don't use randomly. It's actually based on the probability likelihood from the probability part. So it's a quantitative way to measure the uncertainty. Right? So I guess the bottom line here is IPCC does recognize there are different uncertainties in our climate projection or just climate record in general. They try to have 2 ways to deal with uncertainty. Qualitative way using confidence level, and then quantitative way using likelihood, so using probability functions. Right? So when you're reading them, keep that in mind. I think let's stop here for the first part. Really just give you a sense, what IPCC report is, how do they work, and what are the kind of major concepts in climate system relevant